All right. Hey everyone. Welcome back to my stream. Today we'll be continuing with the Learning DSA series and yeah, there we go. So, yesterday we started with the series first of all, right? This is going to be I believe the second stream and first of all we did a summary video on a couple of time complexities, right? So we covered everything from quadratic, linear, constant, exponential, logarithmic. Um, yeah, and there was also log linear, which is I think you might know it more by off and log n. But yeah, and we also coded up binary search, and we stopped that we were going to code what merge sort. So yeah, I see. Let's begin. The lighting is a bit off, isn't it? Recently, well, not recently. I mean, from yesterday, I've been doing these morning streams, and the lighting kind of looks off, but it improves as we go off into the afternoon. But yeah. Anyhow, let's begin.
We'll then create a function,
Let me
which we'll
check if
also call
my
merge.
volume.
The argument to this function is going to be the array that we're looking to sort. For the first portion of this function, we'll need to make sure that the array that we're passing in has a length greater than 1. We will need to do this because if the array is only of length 1 and there's only one element in the array, then it is already sorted.
All right, so I believe we had already covered or at least we saw the code-wise portion of what merge sort is. So I'm just gonna skip this. Basically, we taken an array, right? And then we kind of break the array into pieces, and then after it's broken into pieces, we join them all, together. Oh, we have chat here. Hey, what's up? How are you? From what's that? My screen is quite reflective. Okay, Tija. Okay, it's username, I believe. I'm doing good. What about you? Just continuing with my DSA stream, yeah. Or at least trying to learn DSA. What brings you here? Are you a developer or a student or just interested in programming?
And at that point, arrays of length 1, as mentioned above when we created this base case here, an array of length 1 is already sorted. So to visualize this, if we have an array that is 1, there's only one element in this array. So obviously this 1 is going to be the first and last element in the array. So there's no need to sort it because there's nothing to compare it to. With what we do in this actual merge function is we're going to bring these sorted arrays together and compare them and then sort those individual one element arrays. So one thing to keep in mind throughout the process of writing this merge function is that this merge
This makes sense if the array is a singleton, I guess. Just has one element, then return the array. As we calculate the middle array, the left array, right array, and then we return the merge of that. What's that? Ah, all right, okay, cool. That's amazing. What kind of programming do you do, if you don't mind sharing? Is it web development, game development, or
function is always going to take in two already ordered arrays. It's going to arrays, but compare the two arrays.
all right, okay. We're gonna return the merge of merge sort. So what happens inside merge where Taking the left index as 0, right index as 0. Okay. My left index is less than left array dot length.
And actually,
And we increment the indexes, right? By comparing each and every number.
there's a mistake here. It's just length. I mean, it's never else if you understand.
Else we push the value from the right array and then we increment the right array index and then we concatenate everything together. It's all coming to my mind. Now I guess let's try to build this on our own. So let's see here. Let's create merge.js and then we can get started. So create a function called oh, what's that? You're currently developing your OS, okay? Ah, that's some. I believe that's really not complex, but that's I would say unique. Usually, people say they're building some kind of web app or something like that. That's really cool. I mean, I don't really know much about developing an OS, right? But how do you do it? Is it yeah? What do you use for that? So, let's see. So we need two functions called merge, and then we need, yeah, we obviously need merge sort, right? Or what did he call? Let's name it the same. Yeah, he called it merge sort and merge, didn't he? This would take in an array, and if the length of the array is, oops, misspell length, less than 2, we return the, oh, what's that? I heard some. Oh, thank you. Obviously that's your real name, but thank you so much for following. We're just, I believe, one more follower short from reaching 20. So yeah, it's been some days and we're finally gonna achieve it. Thank you so much, TGRS. So um oops, not this. Let's go back. What are we gonna do now? We're gonna, all right, okay. We check the array or length. It's, if it's less than 2, we return the array. Else I guess we just have to return merge sort left array and merge sort right array. But first let's calculate what left array and right array is. So let's take mid index for that. So that can be math.flow and we'll divide uh we'll divide array.length by 2 and that should give us about the mid index. So unless it's odd, in which case, there wouldn't be any mid index as such. Should I subtract 1 from array.length? Let's just check. Nah, no need. So let's create, oh, actually this should also be, let's do const mid index. Then we can have const left array. We're gonna do array dot, is it splice or slice? I think it's called slice, isn't it? So we do it from 0 to mid index and obviously right. Let's define right array. That's going to be from mid index to the end would be what, array dot length -1, right? Well, actually, the end is not inclusive, right? So we can simply do array dot length. Alrighty, that should do it. And then obviously we return the merge, or we again sort the left array, right array, and then we merge sort it. So basically we're trying to, because of this recursion, this will go down to a level where the array, where it's only kind of comparing a single element. So now let's go back to merge, which would take in, oh, wait a second. Actually, you know what? We'll have done. Oh no, no, that's right. No, no, never mind. Never mind that. So let's have left array defined here. So here's what we're gonna do. Const left index equals it. Left index equals 0. Const right index equal to 0. And here's what we're gonna do. While left index left array dot length, the we have to compare the left index, right? While left index is less than this and the right index is less than this, now we're gonna compare the element in the left index and the right index, and increase the indexes as we move on. Or I guess the plural of indexes indices, or maybe I'm wrong. I'm not sure. Anyhow, let's do this. If left index, all right, if left index left, sorry, if left array left index is less than right array right index, then that means the this value in the left index is smaller, right? So we'll push that into some kind of result array. Let's create an empty array here. We'll call it result. So we'll do result dot push. And then else, yeah, we can have an else statement now, right? Because it doesn't matter if it's equal or greater than, we can just have the right index here. So else we can just result dot push whatever value is in the right array. And let's not forget to increment the value here. So we can do left index plus plus, and here we can do right index plus plus. And once this entire thing is over, we can return the result. Let's put semicolons over there. Oh, I misspelled right array, did I? Yeah, I misspelled it. This should be lowercase. At least the R should be lowercase. So let's just go back and see what we're doing here. If the array has only one value in it, we just return the array because it's already sorted. Else we calculate the mid index, and basically with this logic we're splitting the array into two parts, a left part and a right part. Once that's done, we are going to return the we're going so here recursion is taking place, right? We're gonna um cut the array in half again and again and again until we make sure to get a single element, right? And then we use the merge function that we build out here to sort that array and then return it back to the upper merge function, right? It's like the array is cut into pieces and then it's joined back all together again. We forgot to do one more thing, yeah. We might miss out on, you know, elements here, right? If let's say both right index and both the left array and right array have 3 elements each, right? Or the length is 3 each. And let's just say for whatever reason the left array has all the numbers in the left array is less than the right array. By this logic, all the elements in the left array would be pushed, but the right array would be empty. So to fix that, we're gonna use the concat method for arrays in JS. So what we're gonna do is, let's think here. We're gonna concat to result. What are we gonna concat? We're gonna concatenate left array dot slice. We'll start from whatever the current value of left index is, and end is optional, right? Or is it? Oh, I guess end is not optional. We need it. So anyway, the end would be what? Left array dot length. And we're gonna concatenate the same for the right array. This is to make sure that the elements which are not covered are put into the array, or which were not compared are put into the array. So right index, and let's make sure we're doing this for the right array. And there we go. Alrighty, that should work. Let's see if our merge sort works now. So let array equal, let's have something like this. Well, actually, let's again make sure to use const. Make that a habit. Let's have const output equals and let's see whether the program runs correctly or not. So let's cd into the big O notation algorithms folder. Let's run node moisture.js and into some error. Assignment to constant variable, yeah. Let's change this to let. But I mean, well, not this. This doesn't need to be changed into let. This needs to be changed into let since we're changing the result here. And would this error out because we're trying to push elements into results? I don't. Yeah, it doesn't. Okay, there we go. It's working now. In fact, can we just console.log left array, right array to see what comes up? So we first compare 2, 5. Let's go back. So we compare 2 and 5. We compare 3 and 5. We compare 1, and you can see this is already sorted because of merge sort, right? this array became sorted. This array became sorted, and this was already sorted, came in here, and the algorithm took place and the logic took place for these two arrays, and we finally have our sorted array. And I believe this runs in log linear time, and let's continue with our video now.
By the depth of this recursive function by O of n, which is O of n log n, because O of n log n is just multiplying n by log n, and log n in this case will be the depth at which this recursive function needs to traverse. So let's visualize this merge sort function. We'll go through the code line by line. So let's imagine that we have an array that looks like this. So this array here will be our input array. So this is the array that we're going to pass to our merge sort function here. So this array is this array. So the first portion of the code here, it just checks to see if our array is greater than length 1, because an array of length 1 is already sorted. So if we get an array of length 1 here, we're just going to return that array as an already sorted array. But if the array is greater than length 1, then we're going to move on to this portion of the code. And this portion of the code is where the divide and conquer approach is implemented. So basically here, we're going to split our input array by getting the middle index of the array. We're going to split it into two separate arrays, which will look something like this. And these individual arrays, left array and right array, after they're split, they're going to be once again passed to the merge sort function. And once again, we end up at this portion of the code, because this array and this array are individually being passed to this merge sort function. So for each of these, we end up at this portion of the code. And both of these arrays are not less than length 2. We have an array of length 2 and we have an array of length 3. So they're going to move on to this portion of the code, in which we use the divide and conquer approach once again. And let's go ahead and write that in here, actually, because it's important. So once again, we're going to get the middle index of our array and create a left array and a right array by splitting the single array on its middle index. So you'll notice that this array, and this array are already of length 1. And as we've seen here, we're going to pass these arrays of length 1 to merge sort. We're going to pass these arrays in to merge sort, and then they're going to get to this conditional, and they're less than length 2, so we're just going to return these arrays. So for these arrays, we can stop.
This still gets split, and
Now, these arrays are of length calls to merge sort, but them together into one single sorted array. And what that's going to look like is, it's going to be called here, are going to, and the same things to sorted array, going to be combined. So as mentioned before, this merge function takes two already sorted arrays and it combines them together into one sorted array. And that function looks something like this. So as you can see, merge takes in a left array and a right array, both of which are stand the time complexity of merge sort, earn this result array, which is a combination of both the left array and the right array sorted. So to understand the time complexity of merge sort, we'll take an array of length 4 into consideration. So this input array will pass to the merge sort function. And what that call to merge sort will do is divide the array approximately in half. And those halves will be passed to merge sort recursively.
and I believe is dividing by half is where the log part comes from.
And at this point, we have our arrays of length 1. So we can't split these arrays any further. And to understand the time complexity of merge sort, we need to understand O log n. So as we know in computer science, O log n is the same as log base 2n. And in this case, n is the length of our array here, which is 4. So, and the reason you need to understand log n is because this divide and conquer approach that we're implementing here is log n. That is to say that log base 2 of 4, which is our n is 4, equals 2. And that's because 2 to the power of 2 equals 4, which means that for an array of length 4, there will be 2 levels to our recursive tree structure. And we can see that here. We have level 1 and we have level 2. So this is a level and this is a level. And for each one of these levels, what we need to do is we need to touch every element of n because we need to sort them. And in order to sort them, if you remember from our illustration of merge,
within this merge function, the while loop within this merge function, needs to touch each element to compare the elements and create the merged array. So that means that for each level, we need to merge. And this merge function needs to touch every element of in. So that means that each level is actually O of in. And there are log in levels. So O of in
Becomes
times
and log and or
log in.
log
So this
linear.
means O
Log
of 4,
linear is
because 4 is our in.
sort of a
In
fancy
is
word.
4. 1, 2, 3, 4. So 4 is our in times log base 2 of 4. And as we've seen here, it's in the array and the number of levels that we need to traverse. So for every level, we need to touch in elements in the array, which is 2 times 4. And that's why merge sort has a complexity of O of in log in. 4. Log in is 4. 1, 2, 3, 4. So 4 is our in times log base 2 of 4. And as we've seen here, log base 2 of 4 is actually just 2 times 4. So the number of elements in the array and the number of levels that we need to traverse. So for every level, we need to touch in elements in the array, which is 2 times 4. And that's why merge sort has a complexity of O of in log in.
All right.
So we'll start by examining this recursive implementation of Fibonacci. So let's imagine that we pass the number 4 to our fib function. So at this point, 4 is our value for in. So after we call this function, we'll end up at our first if block. And this if block just returns 0 if in equals 0. And then we move on to a second if block. And the second if block just returns 1 if in equals 1. So once we pass the number 4 into our function, we'll end up at this first if block. And both of these if blocks are base cases because, as we know, with recursive functions, we need to have a base case so that the function doesn't continue to call itself even after we're finished. So we pass the 4 into our fib function, and 4 is not equal to 0, so we don't return 0. And 4 is not equal to 1, so we don't return 1. So we end up here. And what this return does is it adds together the result of 2 more calls to the Fibonacci function. This first Fibonacci function, we're going to call with our in minus 1, so 4 minus 1. And the second one, we're going to call with our in minus 2, so 4 minus 2. So let's have a look at what that looks like. And as we can see, 4 minus 1 is just equal to 3, so this would actually just be 3. And same for here, this would just be equal to 2. So at this point, we have 2 calls to our Fibonacci function, one which we're passing 3 as our in, and one in which we're passing 2 as our in. So for both of these calls, neither one of these will return at these if blocks. So we'll end up back down here again, which will look like this. And again, we can just do the math in the parentheses. And let me just make this a little bit smaller. So at this point, for these 3 calls to the Fibonacci function, we're going to reach our base case because we're passing 0 for this call, and we're going to just return 0 at that point. And we're passing 1 for these 2 calls, and we're going to just return 1 at those points. So these are going to be complete. These ones are done. And for this function, we're passing 2 as our in, which isn't equal to 0 and isn't equal to 1. So at this point, we'll then again go down to this portion of the code. And now these 2 have reached our base cases as well. And one more time, I'll need to shrink this. So now we'll get into the reason why this recursive Fibonacci function is an exponential function. First, let's start by observing this recursive tree structure. So as we can see here, we have 1, 2, and 3 levels to this recursive tree structure. So we can write that out, level 1, level 2, and level 3. And for this first level here, we're calling the fib function 2 times. So 1, 2. And for this second level, we call our fib function 4 times. 1, 2, 3, 4. So this level we make 2 calls to the Fibonacci function, and this level we make 4 calls to the Fibonacci function. And let's just ignore this third level for now, and let's just focus on these top 2 levels. So 2 here is the same as 2 to the power of 1. And 4 here is the same as 2 to the power of 2. And as you can see, our exponents correlate with our levels. So actually, if these 3 functions were to make their 2 additional calls to recursive Fibonacci, we would have something that looks like this.
2 cube.
So we have 2 calls here, 2 calls here, and 2 calls here. So we'll just write this out. So let's imagine that these are also additional calls to the recursive Fibonacci function. And let's just imagine that that's the case for 1 second, just so that we can get a better understanding of why this function is of exponential time complexity. So now if we count the calls at this third level to our recursive Fibonacci function, and keep in mind that these calls won't actually be made, only these ones will be made, but we're just writing this out so that we can get a better visualization of what's happening here. So if we counted out these calls to the Fibonacci function, it would be 1, 2, 3, 4, 5, 6, 7, 8. So we would have 8 calls at this third level, and 8 is the same as 2 cubed, or 2 to the power of 3. And as you see, once again, our exponent corresponds with our level. So that means that if our n is 4, we would go 3 levels deep, and at each level, the number of calls to our Fibonacci function increases exponentially. But you might be wondering, since our n is 4, and we stop here when it's 2 to the power of 3 as opposed to 2 to the power of 4, how does that result in this function being O of 2 to the n? Well, it's actually quite simple. So in actuality, this Fibonacci function is O of 2 to the n minus 1. And if we write this out, you can see it's O of 2 to the 4th power.
Oh yeah. Oh yeah, that's right. And we just estimated to be 2 raised to n.
Power minus 1, which is just equal to O of 2 to the third power, which is the same as the number of calls made at this third level, right? And if you remember, in big O, we ignore constants. So if in actuality this function is O of 2 to the nth power minus 1, and we ignore the constants, that means that we're going to ignore this minus 1, which results in the time complexity of this function being O of 2 to the n. And at this point, you're probably wondering how we're able to add these function calls in here. And in actuality, I only added these function calls in here to give you guys a better visualization of what's happening at each level and why we're considering this function to be O of 2 to the nth power, because it's easier to visualize if we actually write out these functions that we're actually not calling. And we can do that because with big O, as we've learned, we're only looking for an upper bound. Like, we're not looking for a tight bound. We're not looking to be very specific. We're only looking for, you can say, an estimation of the worst case scenario.
Yeah.
So as you can see here, on this left function, we're calling fib, and then we're
It's I think when calculating all these, we should keep in mind that it's an estimate. It's not a like a very specific number for the algorithm, or it's just an estimate. So
we're subtracting 1 from n. And on this right one, we're calling fib, and then we're subtracting 2 from n. So this right side of the tree is always going to be shorter than this left side of the tree. There's always going to be this empty space, because on this right side of the tree, at every level, we're subtracting 2. And at this left side of the tree, at every level, we're subtracting 1. But when we're taking big O into consideration, we don't need to worry about this. And regardless of what number we pass into this function, at the bottommost level, there's always going to be a gap on this right side, but that's okay, because we're only looking for an upper bound. So these are just here to help you visualize what is actually happening and why this function is considered to be of exponential growth. And that is why recursive Fibonacci is of exponential time complexity. I hope that makes sense.
that makes sense. And recursive Fibonacci also, like, just this directly would fail for very, like, not even very large numbers, but it would unless we memorize it. Now, for the purpose of this, I guess I'll just write out the algorithm as such. Well, actually, it's you know what? Let's just put it in the complexities folder. So what we'll have exponential complexity. Well, .js, forgot to add the extension there. .js, and let's just check our binary search. I believe let's just mark the time complexity here. Merge. Well, let's just copy the comment, put it over here. All right. Let's copy this. Let's change this to be exponential. So let's see if n equals 0, return 0, right? If n equals 1, return 1, else we return, it's really a Fibonacci sequence, like computing, right? But let's just name it exponential complexity. Not array, this should take an n, and let's return n minus 1 plus the Fibonacci sequence for the n minus 2th number. And I believe that should work. Let output equal this. Console.log output and we ran into some error and it's not defined. Oh, okay, all right. Let's compute the 8th Fibonacci number, which is 21, which well, let's compute it for ourselves. So it begins with 0, 1, 1, 2, 3, 5, 8, 13, 21. And I guess 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Because the first Fibonacci number is considered to be 0, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. But then would this make this the well, let's just search the Fibonacci series. What number does it start with? It start with 0. Oh yeah, some others start from 1. 0 would be the at least our first Fibonacci number, right? I guess he has considered the sequence to start from 1, but if we want the sequence to start from oops, oops, what did I do there? My bad. 21, 0, 1, 1, 2. So I guess this would be the 0th number. 1, 2, 3, 4, 5, 6, 7, 8.
Initial growth. And that is why recursive Fibonacci is of
Let's see, what is Fibonacci of 4th? Just to make sure this is, yes, consider that comes out to be 3. But is it 3 though? So let's see, we'll add up 1, 1. This would be 2. This would be 3. Yeah, it is 3. So I guess he has considered the sequence to start from 1. Therefore, that makes it 8. But if the sequence were to start from 0, I guess we can just, when we pass to this, right, we would want it to what? Give us the third number, right? If we want the fourth number, if we consider it to start from 1. But you get what I mean. So we leave it at that. Let's go back.
exponential time complexity. I hope that makes sense. We'll start with a function that we'll call f. And this function will be a recursive function. So this first portion of the code is going to be our base case. So if the value for n passed to this function is equal to 0, then we're going to print these stars, and then we're just going to return. But if we pass a value to n that's not equal to 0, then we will go down here to this for loop. So let's start with an example. So let's say that we pass the number 3 to our function. What will happen first is we'll check to see if n, which is 3 in our case, is equal to 0, which it's not. And then we'll move on to this for loop. And what this for loop is going to do is for every iteration of n, for every iteration up until 3, from 0 up until 3, which is our n, we're going to recursively call this function again, this time using our n minus 1. So let's try to visualize this. So
This would call it a total of 3 into 2 into 1.
if we pass 3 to this function and we end up at this for loop, we can write it out like this. So for each index up until 3, but not including 3, 0, 1, 2, to iterate through our if I.
This makes sense.
We're actually call to this function, to this f function. But this time we'll only iterate through indexes 0 and 1. Their own for loop. Still, I'll do this. I apologize a bit. And again, that our a little bit smaller actually, and again, I apologize. So at this point, our for each is only going to happen once for index 0. Oh man, this is getting to the recursive function. And less than n when it's 0, which is this one iteration. So for each of these calls to the recursive function, we're only going to call this function once for this first iteration, which is 0. And at this point, it's going to be f1 minus 1 equal to 0. So it's going to be f0.
You can see it's going to print it out a total of 6 times, right? Which is 3 factorial.
And it's going to be a little bit difficult to see because it's small, but if we remember up here in the actual function, our base case is if n is equal to 0, then we're just going to console log, and then we're going to return. So for each one of these calls to the recursive function, we're going to perform this code, this console log code. And then after we perform this console log code, we're going to return. So it's going to be finished. This entire function will be finished because all of these are going to return. They're going to log the code, and then they're going to return. And once all of these return, this entire
Let's just
function
call
is going
this
to
out
return a
alongside
terminal.
real
So instead
quick.
of writing out console log, we'll just write that each of these functions performs log. And after the log, the function will return. So it'll stop. So for the last time, I'm going to need to make this a little bit smaller. All right, so what we're left with when this function is finished is we're left with this tree structure, and this tree structure shows how many recursive calls that we had to make to get to our base case for each of these recursive calls. And if you look here, I'll go ahead and circle these so that you can see them more clearly. If you look here, for each of these recursive calls to the function, we had to...
Don't we write the every console runs in linear time, right? Runs in cubic type, exponential type. Do we do the same? No, we don't do the same. So I guess we can just console add a console.log here. Which is of 2 raised to n. We have that for cubic, linear, logarithmic, log linear, quadratic, constant. So let's also write that down for factorial. Well, first let's write out the code. So if n equals 0 or strictly equal to 0, let's also make that a habit to use the strictly equal operator every time. I have a feeling that would help us avoid some possibility of errors in the future. So if n is strictly equal to 0, we'll console.log runs in factorial time. Is this even called factorial time or factorial time algorithm? Yeah, it is called factorial time. Else we just return linear complexity. Well, actually it should be in a for loop, right? So for let I equal 0, I should be less than n. We increment I. We can return factor. Well, actually, let's now would be a good time to change the name of the function. Let's call it factorial complexity. Return factorial complexity of n minus 1. Um, that should do it. That should do it. Let's run not factorial complexity. Something happened. Array is not defined. I gotcha. Let's do 5, which I believe should be 1. 125 into 4 is 20, into 3 is 60, into 2 is 120. So yeah, obviously any number times 1 is that number itself. Alright, that didn't run as expected. It just logged. Well, I guess maybe it doesn't, if it's the same statement, it doesn't log it multiple times. Maybe it's not a PowerShell thing, perhaps. I might have done something wrong. Oh, let's see. I listen and oh, we need to return this, don't we? That by that's not the reason. Interesting. What should we do? It's also log n just to test out this theory of ours, but I guess n is always gonna be 0 when it reaches there. Well, no, you don't have to return. You just have to run the factor. Okay, there we go. Alright, that's working now. Although, you know what? Functionality where the same print statement, if the same print statement is occurring, like, you know how in the dev tools, if the same thing appears more than 2 times, a number is put in place for it. Something like that for the terminal would be amazing. Although pretty sure if I dug deep, someone would have, or there might already be some tool which does this. But I guess the debugger does this in a way. But having this for the terminal would be also good.
Is finished is we're left with this tree structure, and this tree structure shows
Of course,
how many
make it
recursive calls that we
optional.
had to make to get to our base case for each of these recursive calls. And if you look here, I'll go ahead and circle these so that you can see them more clearly. If you look here, for each of these recursive calls to the function, we had to perform this code. We had to perform this code. And our factor is we time also our tree test path 1, 2, 3. And so we're going to, because we do 2 iterations for each of these 3. So these iterations plus these iterations plus these iterations equals 6 iterations. And for each of these 6 iterations, we're going to pass 1 to the function. So 6 iterations, so 6 times.
I think at the last chapter we have
times 1.
a segment on space complexity.
Time complexity. I hope that makes sense. So to understand space complexity, we'll take this function into consideration. And this is a recursive function that basically just returns a call to itself with its input in -1. And it's going to do this until we reach a base case where n equals 0. And then it's going to just return, and at that point, this function will be complete. So let's go ahead and draw out what the execution of this function would look like. So let's say that we pass the number 5 to this countdown function.
It would run
so with this
5 times.
Countdown with our argument 5, we'll end up at this base case, and we'll see that our n5 is not equal to 0. So we'll move on to this.
It will run it. It will run it 5 times,
code,
right?
Which is just calling this function again with 5 minus 1. And of course, 5 minus 1 is going to be our into smaller. And finally, we get to the call where we're passing 0 as our in to the function.
Yeah.
At this point, if n is equal to 0, the function will just return. So to understand space complexity, it's actually quite simple. So since this is a recursive function, each one of these calls exists on the call stack simultaneously. So that means that if we call our countdown function with 5, it's going to then call itself with 4. And at this point, this initial call still exists on the call stack. And the same for when we call 3. These 2 calls still exist on the call stack. And all the way down until we reach our base case, every single one of these calls still exists on the call stack. And each one of these calls takes up memory. So each one of these calls existing on the stack, they take up memory. And this is how we come to an understanding of space complexity using this recursive function as an example. Because if we're returning at this point when we reach our base case, that means that we have 1, 2, 3, 4, 5 calls taking up space on our call stack. And 5 also happens to be our value for n. So that would mean that this function, its space complexity is O of n. So this function has a space complexity of O of n. So the most important thing to remember here is that all of these recursive calls exist on the call stack simultaneously, and each one of them takes up memory, which is why if we pass in 5 as our n, we'll have 5 calls existing in memory simultaneously, which means that our space complexity is going to be O of n. It's going to scale linearly with the size of the input. So if we increase the size of this input, the space required to execute this function is going to scale proportionally with the size of this input. So now that we have an understanding of space complexity, we can get into some common mistakes that people make with Big O. And the first one being that when you first start out with Big O, you might see a function that looks like this, that has 2 for loops, and
it has 2 for loops, but it's still gonna be running linear time, right?
You might instinctively assume that this function is of O of n square time complexity, because you see that there are 2 for
Yeah, no, that's wrong.
loops here, so that must mean that's O of n square. But actually, as we've learned, O of n square actually means that for each iteration up until the size of our input, we're going to iterate all the way through an additional for loop up until the size of our input. So what does it mean if we have 2 for loops that aren't nested, that aren't O of n square? It's actually quite simple. So we have one for loop here and we have another for loop here. And as we already know, this for loop would be O of n time complexity. And this one would also be O of n. So at this point, we have 2 O of n's. So that could easily be translated to O of 2n. Which is just O of 2 times n. So 2 times we have O of n. But if we remember from our previous lessons, we ignore constants. And in this case, multiplying n by 2 is just a constant. So we can actually just drop this constant, in which case this just becomes O of n. But there's one important thing that we need to recognize here. This is O of n because we're iterating through the same input for both of these for loops. So as long as our loops are acting on the same input, then this would be the resulting complexity. But there's actually another common mistake that people make when taking time complexity into consideration, which is somewhat related to this mistake. And this common mistake involves having two separate inputs to the function. So let's first take this two inputs add function into consideration. So if you remember from our last example, we only had one input, which was A, and the two for loops looped through that same input. But for this one, you can see that we have two separate inputs here. So we have an input A, which is looped through in this top for loop, and we have an input B, which is looped through in the second for loop. And some people might make the mistake of thinking that this is the same as the last situation where the result would be O of 2n, but this is actually wrong. Because in this particular situation, we have no way of knowing the difference.
Yeah, if at all, it's more gonna be like of A plus B in a way. Or
In size of both of these inputs. Like all we know is that these are two separate inputs. So these two separate inputs could be of either completely different sizes or they could be of the same size. But from our analysis perspective, we have no idea. So in this situation, when we have two inputs and we have a separate for loop for each input, we're going to need to keep track of both of the inputs. So in this case, the time that it would take to loop through both of these for loops is O of A plus B, because we need to first loop through this one up until we reach the value of A, and then we need to loop through this one up until we reach the value of B. And at this point, this can't be simplified any further. We need to acknowledge the fact that both of these inputs are separate inputs. So this would be O of A plus B. And here we have a similar situation.
so if both of these were gonna be, if there was only a single input, it would be A square. So this should be A times B or A
Where we
times
have two
B,
inputs,
something
but
like
this
that.
time the for loops are nested. And a lot of people make the mistake of saying that a function that looks like this is O of n squared. But that would actually be wrong as well. Because what does O of n squared mean? O of n squared means that for every iteration of one input, we're going to iterate through that same exact input. But in this situation, when we have two separate inputs, for every iteration of one of the inputs, we're going to iterate through the other input. So what that means is this is wrong. In actuality, it's O of A times B, because again, we need to specify that these are two different inputs, and these inputs could be of different sizes, and we need to make that visible when we take our complexity into consideration. So that is space complexity and some common mistakes that people make with big O notation. I hope that makes sense.
All right. I think, but obviously the stream as such is not gonna end here because it's learning DSA. It's a wide topic, but I think this was one of the shortest course as such that we've done. Like it was finished in almost 1.5 stream or something. Like the stream is not even complete. So, alrighty, this was a pretty good stream. Yep. So, let's go back and see what we have for us next. So, if you're watching my second stream right now, I already discussed the way that I'm gonna approach learning DSA. And I'm gonna take the roadmap provided by roadmap.sh. Well, where is it? Let's bring that up. Yeah, there we go. So I'm sort of gonna reference this, but at the same time, I'll just switch around between content and yeah, it's not gonna be like any of my previous themes that I've done so far is what I'm trying to say. So now do we understand all of this? Let's check. Big O, yes. Big Omega is the best case scenario, so similar to Big O, but we just provide the best case scenario. Big Theta is somewhere in the middle. Constant, logarithmic, linear, polynomial, which yeah, it's gonna cover what quadratic, cubic, all sort of things. Then exponential, factorial, and they forgot log linear here, I believe, but we also covered that. So with that, yes, we have a very good understanding of what algorithmic complexity is. So first and foremost, let me make sure to commit this. Let's call it completed bigger. And let's provide merge sort. Then what we covered, what did we cover? We covered factorial, then exponential. Let's comment that in. Right, let's move on. Let's see what we should do next. So FYI, I haven't decided this before this stream, so I'm gonna do that live now, I guess. So let's see. Now that we know the what algorithmic complexity is and have an understanding, I think the best way to move forwards is, as you can see, the second part of this roadmap is all about obviously different algorithms and structures, right? And it also covers problem solving techniques. I feel what we should be doing is also there is basic data structures in here, but maybe we'll go into this, but sort of already know what all of these are. So we'll have to see. Okay, we may come back to this. Let's keep that on the table. But I believe what we should do now is let's try to attempt some problems, right? So I think the best way to do this is you can see a section called problem solving techniques here, right? I think merge sort we have already sort of covered divide and conquer. It was the approach used for merge sort where we break the array into singleton arrays and then combine all of them together. Basically, we're dividing the array and then you know combining them all together. Hence, the name divide and conquer. So let's see. There's also a video. It's in C plus plus.
I knew I was underwater. I just didn't realize I was this underwater.
What's going on, everybody, and welcome to Brute Force Algorithm in C++. In this
Okay. I don't understand what I don't understand C plus plus, but well, I mean, yes, I'm at a point where if I look at a code, I can make out what that language is, but I don't. If you ask me to write the application in C plus plus, I won't be able to do that right now. Um, but let's just view this because it's yeah. Let's just look at that. I mean, I understand what brute force algorithm is, but let's just look at this video.
video, we'll be discussing what the Brute Force Algorithm is and how it can be used to
So
solve.
actually, he has made it the thing for 2-pointer technique. Let's just open up the videos real quick. Okay, backtracking is different from another channel here. Oops. Is this being captured on stream or am I screen? Oh, never mind. I thought it was stuck. Thought I lost connection or something. Let's go back. Let's find our own tutorial, I guess. For brute force, let's just follow this. But for the others, because brute force is just for understanding, and I sort of already know what that means. So let's just view that video and then we'll take these topics, watch videos on them, and then I guess solve problems related to that particular algo. Now, before we begin with this, I'm gonna take a quick 5-minute break and I'll be right back with you. Take care. See you in a bit. Alrighty, I'm back. Did you miss me? So let's continue. So let's go into, yeah, let's look at the video for brute force. Although I don't know. I mean, brute force is as you all you already sort of know what brute force is. Right? Like try out all possible combinations, but see.
problems. We'll also go through an example of problem to see how we can implement brute force algorithm to solve it. You usually hear many people say try brute force and then improve upon it. So in this video, we're going to discuss what brute force is
Yeah, I heard
and
of
how
that
you
too.
can start. The brute force algorithm is the simplest and most straightforward algorithm for solving a problem. It involves trying out is the simplest and most straightforward algorithm for solving a problem.
Mhm.
It involves trying out all possible solutions to a problem until the correct one is found. Although it may not be the most efficient algorithm for larger inputs, it can be a good starting point for solving basic problems. Let's consider a simple example problem. Given an array of integers, find the two numbers that add up to the target value. To solve this problem using brute force algorithm, we can simply try out all possible pairs of the numbers in the array and check if their sum is equal to the target value. We can implement this approach using two nested for loops, as you can see. The time complexity of
Why does this? It sort of looks like yeah, and this is C++ way of bringing things right to the console. Sort of looks like JS, to be frank, with the for loop structures and curly braces.
the brute force algorithm is O of n squared, in this case where n is the size of the input array. This is because we are trying out all possible pairs of numbers in the array, which takes n squared iterations. As you can see, we have two for loops. Although this approach works for small inputs, it may not be practical for larger inputs. As you can see, brute force is just brute forcing your way to solve the problem. It's not the most efficient way. You can get it done, and in most cases you want to start solving a problem using the brute force method and then improve upon it. In this video, we discuss what brute force algorithm is and how it can be used to solve problems. We also went through an example problem and saw how we can implement the brute force algorithm to solve it. Although the brute force algorithm may not be the most efficient algorithm for larger inputs, it can be a good starting point for solving basic problems. I hope you understood more about the brute
Yeah.
force algorithm.
Um, find a brute force algorithm first and then improve upon it. Obviously, it doesn't work for very large arrays and everything, but yeah. So let's see. Next, we have backtracking greedy algorithms. So out of this, I sort of more or less know. I mean, I've heard of most of them. I haven't heard of randomized algorithms. Um, all the sliding window technique, but others I've heard or sort of know what they are. Yeah, I've heard of backtracking. There's a video given here and
MBBS സ്വപ്നം കാണുന്ന
a difference between.
വിദ്യാർത്ഥികൾക്കായിട്ട് നീറ്റ് ക്രാഷ് പ്രോഗ്രാമായിട്ട് സൈലം നിങ്ങളുടെ മുമ്പിലേക്ക് എത്താൻ വേണ്ടി പോവുകയാണ് ഓൺലൈനായിട്ട് ജാനുവരി 15 മുതൽ നിങ്ങൾക്ക് ജോയിൻ ചെയ്യാം.
React is a free and open source front-end JavaScript library for building user interfaces. If you are in a
हाय गाइस, वेलकम बैक टू द चैनल कोड इंटेन। आई एम निशांत चार। तो आज की वीडियो में हम बात करने वाले हैं बैक ट्रैकिंग के बारे में। ठीक है, बैक ट्रैकिंग में हम रिकर्जन ही यूज़ कर रहे हो।
Oh, this video is in Hindi. I mean, I understand Hindi, but let's look for another video here. Backtracking. Ooh. Cam has literally everything any developer could ask for.
a software engineer at Salesforce and an excellent teacher. In this course, you'll teach you how to solve backtracking problems, which are common in coding interviews and challenges.
Hi everyone, I'm Lee. I'm a software engineer, hobbyist game developer, and recent graduate from the University of Chicago. Welcome to this course on solving backtracking problems. Whether you
Okay, I think we'll use this to get an understanding of what backtracking is and solve some problems alongside. And then now this is something I've sort of looked over. Right, Geek for Geeks website has they list out problems for all sort of all the problem solving techniques. Or I haven't checked for all, but most of it is in there. And you can always Google if something isn't in here, right? So let's do this. We're gonna cover this, right? Let's see how to implement this, and then we'll take some problems on our own which sound interesting and try to solve them on our own. And yeah, let's do it that way. Oh, actually, I've been. Can you sort for problems on Codverse based on? You can do it based on topic, but can you do it based on algorithms and whatnot? Tags, okay? Is there gonna be backtracking in here? Wonder why AI is given in here. I guess it's like related to the problem statement, like the story or whatever that using to explain the stuff. Let's see. There should be. Yes, no. It doesn't give you backtracking as such. I mean, could you possibly? Oh wait, there's algorithms in there. I mean, can you search for? Okay, let's do backtracking. Search for it. Oh, all right. I expect that to happen. I believe LeetCode. I believe LeetCode has some kind of option like that, or at least some sort of option like that. Let's check. Backtracking LeetCode. Plus problems to practice. Nice. I mean, if this. Ooh, there you go. That's pretty neat. I have not made a Discord account for the stream yet. I mean, I have one, but I haven't made one for the stream. I may do this. Okay. Let's focus on this for now, and if time persists, we can think on how to do this. So
you're new to coding interviews or already have experience with backtracking problems, this is the crash course for you. We will learn about an all-purpose template that helps you solve any kind of backtracking problems, and we will apply the template to LeetCode problems like the 8 queens problem or the Sudoku solver problem. This is exactly the template that I use for my coding interview problems when I'm developing algorithms for my games, or even once in my research on a non-convex optimization problem. I hope you're excited, and let's dive right into this versatile template. You can find this template in my GitHub gist linked to in the video description below. Let's start with some keywords and concepts in backtracking problems that will help us understand the template better. The first keyword, state. Essentially, a backtracking problem is asking you to find valid states. Take the n queens example that we will solve later in this.
Yeah, again, this is a so I kind of already knew about the n queens problem, not through programming. This was way back before I even knew what programming was or any sort of programming language. Um, so I, I was really fond of chess. I still am. I do, play it and stuff. But this was a problem given to be my coach, and he asked me to place queens in the squares or find a possible possible combination in the chessboard where you can place the queens and they don't then they don't become a target of one another.
Video. An example of a state is just arbitrarily placing n queens on an n by n board. For example, here we are placing 4 queens on a 4 by 4 board.
G85 5G प्राइस सेगमेंट में सबसे अच्छा फीचर रिच फोन है
with incredible features.
जबरदस्त डिजाइन 3D कर्व्ड POLED डिस्प्ले आता है सबसे अच्छा 50 मेगापिक्सल का OIS कैमरा आता है Sony Litia 600 सेंसर के साथ
Flagship features like smart connect to share,
one of the best 5G smartphone.
Hello, Moto.
On the contrary, an example of a valid state requires that the queen are placed in a fashion that they cannot attack each other. If you aren't familiar with the rules of chess, don't worry. The moves of queens are pretty straightforward. A queen can move horizontally, vertically, or diagonally. Therefore, for a replacement of the n queens to be valid, they can't stand on the same row, the same column, or the 2 diagonals. So how do we construct a valid state like this? Well, we build up from previous states. Suppose we're starting from the blank n by n board where no queen is present. We can put our first queen arbitrarily wherever we want. Let's say we put it here. Then where can we place the second queen? You can see now our choices are limited, or in background terminology, our candidate states are limited. Because we place the first queen here, this entire column, this entire row, and the 2 diagonals are now unavailable for new queens. Let's say we just put the second queen here, where it's available. Next, we try to see where we can fit in the third queen. Our candidates are now more limited because we put the second queen here. This column, this row, and this diagonal is not available. So our third queen can only go here. Finally, let's place the fourth queen. Because this third queen is here, it blocks this diagonal, and this row and this column, leaving our fourth queen to sit here. Great. Now, is this global layout a valid solution such that no queen can attack each other? Well, we've already seen in our
Yeah, it is, right?
checks. So like this, we have found a valid solution to this n queen problem. As a counterexample, consider if we place the first 2 queens like this. Now, all these cells marked in red are unavailable, and we only have 1 left for the third queen, and nowhere to place the fourth.
So I guess we backtrack. We just say, okay, let's not even go forward and calculate the rest of possible combination for this state. And we move up the tree. Basically, we remove this queen and try to place it somewhere else.
Queen. This means that this succession of state searches fails to lead to a valid solution. And this is pretty much it about states, identifying candidates to build the next state and validating a final solution. Now let's look at how these procedures are defined in our template. There are 4 functions in our template. The first 3 is valid state, get candidates, search, are helper functions. The last and most important one, solve, is the entry point to our program. The solve function is indeed the one that a LeetCode problem is asking you to write. It is responsible for returning the valid solutions.
It's valid state, okay, makes sense. Get candidates, all right, okay, based on whatever state we give it. Then it has search. I like how she's using Python for this. Yeah, I didn't check beforehand whether this video is done in a language which I can follow through, but yes, even if it was a different language, we could sort of make it out. So, but I'm glad she's using Python, yeah.
Let's look at the helper functions one by one. This valid state. This function takes in a state and returns a boolean. It validates whether a state can be used as a final solution. In our queens problem, a state is a validated solution if all n queens are placed on the board and none of them can attack each other. Get candidates. This function finds a list of candidates that can be used to construct the next state. Search. This is a recursive function. It calls the previous 2 helper functions and checks if the state is a valid solution to our backtracking problem. If it is, it records the solution by making a deep copy of the state. Note that we do need a deep copy instead of a shallow copy because we will continue to modify the state as our search goes. But we need a static snapshot of the valid state here. This line of return is commented out because depending on the nature of the problem, we might need to find all valid solutions or just one. If we only need one, we can return as soon as we have found it. Otherwise, we continue on until we exhaust all the possible search states. Continue down here. If the state isn't yet a valid solution, we find candidates to build the next state. Recall that getCandidates return a list of candidates. For each one, we add a candidate to the state. In the queen's problem, for instance, suppose our state only contains the position of the first queen. Here, we add a candidate position for the second queen. Now we take this modified state and recurse on it by calling the search method on this modified state. If the modified state is valid, the solution is recorded, like here. Otherwise, the search function.
Else we I'm gonna assume we place the second queen in here, right? But obviously we need to place 4 queens, so we add that as a possible candidate, and then we perform the search again, and then we remove the candidate, right? Yeah. Okay.
Fetches candidates for this modified state and recurs further. Eventually, for some state, there is no more possible candidate. Think that example where we cannot place a 4th queen anywhere because all the spaces have been occupied. After returning from the recursive search, we restore the modified state to the original by removing the candidate from the state. Again, the queen's modified state to the original have been occupied. After returning from the recursive search, we restore the modified state to the original by removing the candidate from the state.
So state is the set, and we remove the candidate. Yeah, because we have already kind of validated that candidate, right? If that candidate is a solution, then it would already be appended into solutions. And if it's not a solution, it's still a candidate, we proceed onwards with the search. But my question is, when do we, I guess when we pass the that state into get candidates, it will do the logic of whether to evaluate the state or not, right? So
again, in the queen's example,
okay, sort of making sense. Let's continue.
As for solve, it starts with an empty list of solution and an empty state. It calls search on the state and this list of empty solution. Search will eventually fill up this list of empty solutions and then return the list of solutions. And remember, this is the function that LeetCode problem is asking us to write.
G85 5G इस प्राइस सेगमेंट में सबसे अच्छा फीचर रिच फोन है विद इनक्रेडिबल फीचर्स जबरदस्त डिजाइन 3D कर्व्ड P OLED डिस्प्ले आता है सबसे अच्छा 50 मेगापिक्सल का OIS कैमरा आता है Sony Litia 600 सेंसर के साथ फ्लैगशिप फीचर्स लाइक स्मार्ट कनेक्ट टू शेयर वन ऑफ द बेस्ट 5G स्मार्टफोन हेलो मोटो.
When using this template, keep in mind that this is only a template, so your helper functions is valid state, get candidates. They might take in additional parameters. Search might also return a boolean indicating whether a solution has been found and return early if there is one and only one valid global solution, like in the Sudoku problem that we will eventually see. This concludes our brief introduction to the template. Next, let's solve the queen's problem hands-on in LeetCode. Here we are on LeetCode number 51, the n queen's problem, which is a LeetCode hard problem. Let's first read the problem statement. Given an integer n, we want to return all the distinct solutions to the n queen's puzzle, and we may return the answer in any order.
Then queen's puzzle is, yeah. Is the n queens? I mean, it's a common problem, right? It should be there in Code Wars. Oh yeah, that is the problem. Yeah. Hold on a second. I'll be right back. Give me 2 minutes. Alrighty, I'm back. So I feel I'm gonna end the stream right now. And then yeah, I'll see you in the next one. I'll make sure to create a lead code account, set everything up, and then yeah, let's continue with that. Alright, people, take care. See you in the next one.